Well, good afternoon. I'm Meredith Lecocke from Southwest Research Institute in San Antonio, Texas. And I don't have anything nearly as exciting as dying in a big ball of fire from an asteroid impact, but I hope that at least it's better being in here warm and dry than outside in the cold and rain. So my topic is formal modeling for FDIR, basically fault detection, isolation, and response. We feel that this internal research project had a lot of advantages and gains compared to the traditional approach, and so that's what I'm here to talk about. Hopefully you'll learn something. So the general setup is a highly fault-tolerant, too fault-tolerant in this case, system, and in our case it was a manned spacecraft, but this could also apply to some kind of robotic spacecraft doing critical operations, maybe with the space station or in some sort of close rendezvous operation that could damage critical assets. So you have this reliability requirement that's usually addressed with an FDIR process, fault detection, isolation, and response is what FDIR stands for, or FDIR, or FDIR, or many other pronunciations. And the general idea is to identify all the possible faults in the system of any sort and prove that you have some method in place to handle that so that you don't lose your mission or your astronauts. So here's a very simplified block diagram of our system. In our case, we had some redundant nodes, all of them talking over various kinds of networks, and the end goal was to drive an arm into some position with both sides driving it simultaneously for best performance. And so, as you know, there's all different kinds of ways things could go wrong in the system, from network faults to single event upsets to hardware breaking down or whatever. And so to be dual fault tolerant, you have to handle any two of these, two of the same kind or two of a different kind, simultaneously. So, let's see. Okay. So the general traditional approach is to use a fault mode analysis, an FMA process, where you go by hand and analyze your entire system to come up with all the different signals in the system and then all the different ways each one could fail, stuck high, stuck low, stuck floating, get a bad message on a network, those kinds of things. And then classify them by criticality. So what you really care about is which ones are going to cause my astronaut to die or my critical asset to be lost. So you're pulling together every piece of documentation you can find and putting it all into some massive system. In our case, it was a spreadsheet. And so we had an FDIR FMA expert with decades of experience, plus all of our engineers working on this for about 18 months, and we only got through the single fault modes. And so that's the traditional approach. And then what I would like to present to you is a parallel effort that we did that we feel is better. But first, the traditional. So we had this massive spreadsheet, and you're not intended to be able to read that. It's just one line of about 616, just identifying our 187 different signals and all the different ways they could fail, just one fault at a time. So then you would need to also go through and do all the permutations of the two faults of all those different kinds. So of the single faults, we had 423 that were critical, meaning we would kill the pilots or destroy the space station or whatever. So all of those had to be, we had to prove that our system could handle that and not cause these problems. And so you can imagine that quantity of things trying to get right, trying to keep it all straight in your brain. Did we think of everything? What impact does each thing have on the other? It's just rather untenable for a human brain. So that is where we came up with this idea that we did with some internal research in parallel to the traditional approach was, well, we know human brains have trouble with that much quantity of information and keeping it straight all at once, but we know computers are very good at that. And so what if we could leverage the power of the computer to do all of this difficult permutations and computations for us and let us just keep our brains working at where they do well at a higher level of abstraction. So that's where the formal modeling came into play. So I'm not a formal modeling expert, but my colleague is, and so together we worked on this project. And the general idea was get our system into this formal model where we can get the high-level ideas straight. We can keep 30-ish items straight in our heads. We can handle that. Also, it allows us to communicate much better with the rest of the team. And then we can let the processor, on a regular desktop PC, crunch on all of these different permutations and prove whether I've handled every single possible two-fault scenario. So the rest of this presentation is talking about how we did that. And we used answer set Prolog, which is a knowledge representation language. And it allowed us to specify all of our different components, all the interactions between them and the states and faults that could occur. And I'll go into more detail about that. And then the goals, how we want to accomplish our ultimate mission of moving our arm, and as well as prioritizing them. So the top priority would be move the arm using both sides so you get top performance, if at all possible. And then, of course, there's a degraded mode. You could still move it with just one side. And then the worst case would be a fail-safe mode where you just lock the arm down and don't let it damage anything else. But clearly you don't want to go straight to that. You want that to be your last resort. So, and then once we have it all specified, we can let the PC process all the different permutations, find paths through the system to work around faults and things like that. So here's the beginning point of our model where we specified all our different nodes and interactions and wires. That part is pretty easy. It gets more interesting when we start talking about actions. But first we had to define our different states. And for us, for simplicity, for just learning how to do this FDIR process, we kept it at a Boolean state. It was healthy or not healthy, received a command, didn't receive a command. With the idea being that you would have something in front of that that would consolidate your health and status information into a thumbs up, thumbs down on a given Boolean state. And then specifying all the actions, so all the things that the system does. It sends a command from here to here. It tells the arm to move there, all those sorts of interactions in the case where there's no faults going on. So that then you can define what faults could happen that would prevent those actions from having their desired effects. So this is all just in the answer set Prolog. You're writing logical representations of these rules, basically, saying that in the absence of a fault, flight computer FC can send a message to control board CA1, and the result is CA1 has the message. And then you have another rule somewhere saying, but if the wire between the two is broken, the result is CA1 does not have the message. So it's all very simple, when you're specifying how this works. It sounds kind of dumb, but once you've got it all specified, now the computer can reason through all the different combinations of what happens. So that's where the power of it comes in. And then here's the goals I was talking about, where you have prioritized levels of what you would really like to achieve. So ideally, if you can keep driving it with both sides, you want to keep doing that. So if you could imagine, like in our system diagram here, if CA1 died, you could still drive it with two sides of the arm, because you've got CA2 that can do things on that side, and the other side is still fully functioning, something like that. But if, say, motorboard MB dies, you can't drive that side anymore. So there are various things like that where you have to choose the best possible outcome, and so these are ways that you define those rules for the formal model so it can make a good choice. So that kind of just said that. And then, to me, as the embedded person, the most exciting part was that once we have this model in place, which we've now verified and run all of our permutations and proven that we have a path to success for any two-fault scenario, now I can automatically generate some algorithms, well, not even algorithms, a very simple Boolean lookup table that I download to my actual target processor that's running on the spacecraft. So whereas before I had all these complicated algorithms of if this, then that, what if this happens, then take this route, or maybe a big switch statement or a state machine or something, now all I have is Boolean state arrays that I put together and say healthy, not healthy, whatever, match it up to a line in the table, execute the plan that goes with that. So it's much simpler. It also it simplifies verification. If I can prove that these tables match the verified model, I've got that part covered. Now I have to prove that my algorithms running the table are correct. But it's much simpler than verifying 423-something fault tolerance methods. So I kind of said that already. So here is an example. If you were doing the fault detection, isolation, and response process in the embedded processor, what it would look like. So there's just some little dev board over there, but you'd have real flight hardware, of course. And you have two sets of tables that have been generated from your formal model. One is for fault detection, so it takes all your possible combinations of two fault scenarios. And the other one is your fault response, so it's going to tell you what action to take given that state. So hopefully you're spending all your time in the no-fault scenario running your nominal plan most of the time. But if something should happen, in this case we've said we detect a sensor mismatch. So I get a Boolean saying false on your sensor matching health status. So then I can look into my fault detection table, match up that status, and it says, well, if you've observed this, then either that wire is broken or that component is faulty. And so then I can go do some more analysis, some little tests. I shouldn't be saying me. The processor can go in, run some more tests, and figure out which one it is. So that's your detection and isolation process. And now it's got an updated fault set. So now I'm running with fault set saying CA2 is faulty. And so then I use that as my index into my fault response table, and that tells me, okay, if CA2 is faulty, then you're going to route around it, and you're always going to use CA1 because these happen to be redundant. So that's just one example, but it's showing how the software isn't having to go through all the possible branches of all the different things that could be wrong and find all the combinations. All it does is reference into these tables. So I like the simplicity of it. It also makes it much easier to test. So the main takeaway that I wanted to bring to the group here was that we felt that this was a much better approach. I mean, it's obviously still in its infancy, but compared to our 18-month times 6, so 18 times 6, however that is in man years, to just get the single fault cases addressed, we felt this was a much better approach. We felt more confident in it in terms of claiming actual two-fault tolerant reliability. The system would also, and this did happen when we were first starting and didn't have everything in place in our system, the formal model would actually spit out and say, you have no plan to address this fault scenario. So that points out to you where you need to add a circuit, or you need to add an algorithm, or whatever. Maybe you need a redundant node, something like that. And so we felt that being able to model all of this early on, it's independent of hardware development. It's much easier for all different sorts of people to understand, the systems engineers, the software engineers, hardware, and it's a lot fewer things to get right. And so we felt, that's why we felt more confident, was that we can get this 19 actions and 10 faults and whatever the combination of those comes out to be, but it was much easier than 600 something or another faults that we had identified. And the verification of the full coverage was, I thought, a real win, because the traditional approach, coming up with a way to test all of these fault modes, in some cases completely impossible. You cannot force it into that fault mode. But even if you could simulate it somehow, that's an awful lot of tests. So being able to verify it at the model level and then prove the matching implementation on the embedded side, I felt was a big win. As well as it being easy to change. If we decided to add another node, or we decided to change how it responds in a given fault mode, all we have to do is download a new table rather than changing the algorithm in the software, and then now we have to revalidate it and all that kind of thing. So there's a lot more work we could do to compare the two methods, but so far we find this to be a much better approach, and I wanted to get it out there to the world and hope that others could maybe try something similar. So, are there any questions? Okay.
believe you're shortening the span.
I have a lot of questions, so let's see. I'll try to pick one or two. The tool that you used, ASP, first of all, is that, I didn't see any diagrams of what that looked like or how easy it was to use, how easy it was to change inputs, and if it's
Could you, is that not? Tap it, see what happens. Tap it harder. Sorry. Here, take this one. This one's full page.
That's the redundant unit. So one question would be the tool that was used, ASP. I didn't see a lot on if it was easy to use, if that was a good option, if there were other options that were assessed, if it's a commercial product or available. Another one would be, it seemed fairly straightforward that the end product that you said this lookup table, but that was for a fairly simplified system and a simplified way of looking at that system. So have you guys thought about, or maybe you've come up with a way to determine how well it actually would scale to a more complex system where you want to consider not just signals, but common sources of failure that cause multiple simultaneous signatures? For instance, how do you separate those? So you know what I mean. It's one reason it might have appeared simplified at the end is because you were using a simplified method. So I'm wondering, the scalability. It still is an improvement from the manual method of deriving that product. So I guess I'll just leave it at those two for now.
So ASP, I think, is out of Cornell. It's definitely an open source tool that anybody can use. There certainly are others, but I think I may have it in here that ASP has been used in some other aerospace applications, which is where my colleague had encountered it. So we did not evaluate different options for that. What were your other questions?
Second question was, have you thought about the scalability? In other words, you said the end product was a simple lookup table, and it was small in size. For instance, it wasn't exactly clear what you meant by embedded. If it wasn't handled by a real-time operating system, or if it was what was meant by that. But if your end product potentially is going to be much larger in a memory map size, for instance, when you're dealing with a real system, which is much more complex than the block diagram that you had, and within that system, when you actually want to dive into common sources of failures, like an IC fails, it affects multiple signals, not just one signal at a time, those sorts of things. So have you looked at, what happens when you suddenly scale it? Because in fault management, this is a problem we have is, rule-based system is fine. When you try to scale it, it becomes unmanageable. So
Right. Yeah, so this block diagram actually does represent our system well, but one thing we were exploring was how fine a grain of detail do you want to go down when you're analyzing this. It will do the common mode effects, so if you have one part that fails and it impacts multiple things, it will show you that. It would be interesting to maybe explore what level of detail you want to take it down to. From the flight software perspective, this was sufficient. So that was what the algorithm running in the processor needed at a level of detail. Because a lot of the things like at the circuit level were handled with the hardware already. But it would be interesting to use it for both. And then, of course, the downloadable lookup table thing is irrelevant to the hardware guys. They're just having it analyze for them where they need to add circuit protections or whatever. But for me, as the flight software person, the tables handled all of the inputs, and they're much bigger than what I showed here. I just made it simple for the display. But so if you imagine like lots of columns of all the various things that I'm measuring to see what state of the system is, and then all the different permutations of those, So I think it scaled well in terms of what this embedded processor was doing. I didn't really think about how it would scale to something outside of software like the hardware implementations.
or just a larger, more complex system.
Right.
Okay. Other questions? So, is it, your recommendation is to complement the traditional approach with this model-based, or is it, should we replace the manual approach with this model-based fault designing?
Well, at least from the perspective of the things the processor has to handle in software, we thought this was a better approach than the manual.
So I think it goes back to his question. I mean, have you considered all, it depends on the complexity, right?
Yes.
And have you covered all the states, and have you covered all the rule-based within your model? Pretty much those dictate or drive your fault design.
Right. We have, from the processor's worldview, as far as all the other aspects of the system, we haven't tried it for that.
Did it have any real application?
Yeah, so we would have liked to have gotten to another phase on this project. We haven't gotten that awarded yet. But as far as we got on this project, we were implementing this on a real embedded processor. You had asked about an RTOS. It is running one, but that's kind of irrelevant to this algorithm. It wouldn't have to be in an RTOS.
Thank you.
This is a very nice approach, but it kind of depends on the quality of the models. So how did you verify the models?
Right. So I think I said that somewhere, that obviously you are still susceptible to human error. You still have to identify all of your fault potential correctly, and if you miss it, it's still going to be missing from your detection methods. But we felt that getting it right at a higher level of abstraction was more likely than us getting all these low-level signals correct. How did we verify it? So we have the model represented as a block diagram as well as in the textual ASP, and basically reviewed it with systems engineers and that sort. And then you can automatically verify that you've covered all of the fault scenarios by running the formal model.
Okay, we have one more here.
This looks very interesting, and this might be something for future work, but in this case you did the sort of engineering grassroots method in parallel with the higher level model base. And it looked like the engineers came up with 600 and some fault scenarios, and the model came up with 500 and some fault scenarios. And I wonder if there's a mapping between those where you can see if the grassroots found some cases that were important by looking at the level of detail, or if they just don't match up at all.
Yeah, I would like to do it exhaustively. What I've done so far is sort of sanity checks, that we've covered this general scenario that we already knew we'd found in the traditional approach. One thing I think you said was, I would really like to see, did we find some that we didn't find in the traditional approach? The numbers, the 616 versus the 543, those aren't apples to apples, because in the model we're talking about a higher level. So I'm just looking Boolean, healthy, not healthy, whereas the 616 is all the various ways it could fail. So there could be 3 or 4 different ones that I would have, at this level, combined into one. So this, yeah, there is a mapping, but it's not evident from what I put up here in the slides. But so the model did, in fact, find more than we found in the traditional approach. But that's one thing I would really like to do, is go and map them together and see where the gaps are.
Okay, any other questions?